In this problem, we have a box accelerating down an incline, and we're asked to find the kinetic coefficient of friction between the box and the ramp. As with any dynamics problem, it starts with a free body diagram. So I'm going to draw my ramp surface. Now, technically, again, a free body diagram does not include anything except the mass that is accelerating, but it can be helpful to have the surface itself on there. So there's my incline. I'm going to draw the box on the incline. And we know that this box has an acceleration down the ramp. Now, one thing we can do with an incline problem is to simplify the direction of our acceleration. It'd be confusing to have an acceleration at an angle. So rather than having the acceleration angle, let's reorient our axes. And we're going to say that down the ramp is now my x direction, and up away from the ramp is now the y direction. And so that's going to simplify some things. That's going to mean my acceleration is now down the ramp, and it would be an x acceleration. All right, so now we've kind of redefined our direction here. I'm going to put in the angle of this ramp. This is a 30-degree angle. And when we start to draw the forces, you'll see why it can be beneficial to reorient our x and y directions in this way. But indeed, this is an object that is accelerating. The first force we're going to typically put on a free body diagram is going to be that force of gravity. So Fg acts straight down towards the center of the Earth, and that actually becomes our angled force. So it might be helpful at this point to draw the pieces of Fg. So this is Fg, our weight, and some of Fg acts perpendicular to the surface, and we call that Fg in the y direction. And some of that acts down the ramp, right? And as we do with vectors, I can put that down here, and here's where you might see that triangle. I've got a right angle right here, and I've got an angle in here that is actually now the same as the ramp angle. That is 30 degrees. So we have the force of gravity straight down, but we're going to look at those pieces of gravity, those components, the x and y pieces, to actually analyze this object. So once I know them, now I can figure out what the other forces are going to be. So we know we have a normal force, right? And since the normal force is from the ramp pushing back, it is always perpendicular. And now that we've drawn that y piece of gravity, we know that the normal force would have to be the same length as that y piece of gravity. Now, because it's not accelerating in and out of the surface. And now we can also draw friction. This is accelerating down the ramp. So gravity is the force that's making it go down the ramp, but it's only this x piece of gravity. So friction is going to have to be less than that x piece of gravity. So here we have our free body diagram. You effectively have three forces, but we've broken gravity into pieces, right? So how we're going to set up the problem from here is we're going to organize all these forces. And Newton's second law says that the sum of all forces is equal to m times a. And as we do with dynamics problems in two directions, we're going to break it into the forces that act horizontally and the horizontal acceleration, and all the forces that act vertically and that vertical acceleration. So we've now broken it into two different problems, and we're going to separate out the pieces. So in the x direction, this is the direction along the ramp surface. You would have a mass. You would have an acceleration along that ramp surface, and you have forces that act in that direction. One of those forces now is going to be Fg in the x direction, and the other force is going to be the friction force. All right, and we want to find mu, so friction is going to be one of those pieces we need to find mu, and we'll come back to that here shortly. And let's go back now to our y side here. And the y side, again, you have a mass, you have an acceleration in the y, you have, once again, gravity, but this time it's gravity acting in the y direction, and you have the normal force. All right, so I'm working this thing through. Now, again, if you look at your free body diagram, you might infer what those forces would have to be once we start to calculate them, but this is a good way to organize them out. All right, so what next here? Well, they tell us something about the box. This box has a mass of 10 kilograms. Again, when they give you kilograms, they've given you the mass. And with the mass, we can calculate what Fg is. Fg, the force of gravity, is always equal to the mass times the acceleration due to gravity on Earth. Right? So the amount of it would therefore be 10 times 9.8, or 98 newtons of force. And again, it's straight down, but in this case, it's actually at an angle because we've turned our x and y axes. Well, then how do we find those pieces of gravity? Well, if you look at that triangle and we try to find the pieces, the x piece is the opposite piece to that 30-degree angle. And we have the hypotenuse FG, which is now 98. We're going to write 98 in here. So FG and the x, we're actually going to use the sine function to find that. And so we're going to do the sine of 30 is equal to FG and the x over 98, or 98 sine of 30 degrees is equal to FG and the x. And that's going to be down the ramp. Sine of 30 is 1/2, so we have 49 newtons of gravity acting down the ramp. A good way to remember on ramp problems is that sine slides. The sine of the ramp angle will always give you the piece of gravity that makes it slide down the ramp, which means that if we want the y piece of gravity, we're going to be doing 98 cosine of 30 degrees. I'll break out the calculator for this one. We have 98 cosine of 30, and that's going to be 84.9. 84.9 newtons is how much gravity is acting into the ramp. So I'm going to put those pieces in here. Again, down the ramp is positive, so the x piece is positive 49 newtons, and the y piece is into the ramp. That's going to be the negative direction, 84.9 newtons. All right, so where do we go from here? All right, well, let's plug in the things we know in our table. We know the mass is 10 kilograms. It accelerates down the ramp, so positive, at 3 meters per second squared, which means we have one missing piece. We have F, force of friction. And on the y side, you have the same mass. However, it's not leaving the ramp surface, so we have no acceleration, which means that the sum of these two forces has to be 0, which means the normal force better be the same as gravity, which we have that already in our free body diagram. So I have the normal force as 84.9. So how do we find friction? Well, this is where Newton's second law comes into play. We know that the sum of the forces acting in the x direction, Fg, plus friction, get my colors here, has to equal the mass times the acceleration in the x. And gravity is 49 newtons. Friction is what we don't know. We need to find friction if we want to get to mu. And that's got to be equal to 10. And the acceleration is the ramp acceleration, which is 3. So again, we have 49 plus friction is equal to this net force of 30, which tells you that friction would have to be acting up the ramp at negative, right, which is what up the ramp would be, 19 newtons. So we now know that friction is 19 newtons up the ramp. All right, so we have the pieces we need here, and they want the coefficient of friction. So it's sliding, and we know that the mu is always equal to the friction force over the normal force. And I like to put the absolute value bars on there because it really only cares about how much friction, right? We have negative friction in this case, but if we decide to call up the ramp positive, then friction would be a positive force. So we're going to put in what we have here for friction. Friction is 19 newtons. The normal force is 84.9 newtons. I can pull out my calculator and do that little bit of math. We get 19 divided by, there's 84.9 up there. I'm going to do second answer, and I'm going to get 0.224. 0.224 as my coefficient of friction. Again, it's kinetic friction because we're sliding. And there's our answer. So, not a lot of friction here. It's got a pretty good acceleration down this ramp at this ramp angle.